Hello everyone, my name is Ian, and I'm going to be helping with the organic chemistry lab this semester. And this first lab we're going to be doing is the fractional distillation. So before we can talk about what distillation is, we're going to have to discuss certain terms. And some of these terms may be familiar and some of them not, but we're going to go over all of them so we're all on the same page. So the first term is boiling. So boiling is something we've all seen whenever you've cooked something or made coffee or made tea. And boiling is simply the transition from a liquid substance turning into a gas. Now the next term we need to discuss is vapor pressure, and this is one we probably haven't heard of. So the vapor pressure of a substance or a liquid is the pressure that is exerted by its gas phase. So here, if we have a closed system, such as a bottle or maybe a cup that's sealed, obviously you'll have water molecules or other types of liquid in the bottom phase. And these exist throughout the mixture, and they are relatively uniform. Now, accompanying this liquid phase is a gas phase, but the gas phase is much less dense. There are much fewer particles compared to the liquid phase. To understand this more better, maybe we can examine a beaker of water. So the old adage is that, well, is the glass half full or half empty? Now an optimist might say the glass is half full and the pessimist says it's half empty, but a chemist says that the thing is full because it has both a liquid and a gas at the same time. So in this beaker you have a liquid phase, but also above it in the headspace is water vapor. And the pressure that it exerts on the walls of the beaker is called the vapor pressure. And all liquids have a vapor pressure. So in general, as the temperature of a liquid increases, so if you were to heat it, the vapor pressure will also increase. Now the opposite is also true. If you cool the temperature or you lower the temperature of a liquid, the vapor pressure will also decrease. And this is due to the particles in the liquid having more energy. So if you heat this liquid to where it has more particles and it can escape the liquid phase into the gas phase, there's going to be a higher vapor pressure. Now the boiling point is an interesting phenomenon, and boiling point is the temperature at which the vapor pressure will equal the external pressure. So for example, at sea level, water will boil at 100 degrees Celsius. And that is the point at which the water's vapor pressure is equal to the external pressure. Now the final term we're going to discuss is volatility. So a substance which is said to be more volatile, in general, has a lower boiling point. And the opposite, a substance which is said to be less volatile, in general, has a higher boiling point. So now that we've discussed these terms, we can look at a certain example which is relevant. So say for example, we have 3 pots, one in Denver, Colorado, one in Honolulu, Hawaii, and one which is a pressure cooker. And say we want to boil some potatoes in there. So I'll place some potatoes into the water. And let's examine how these potatoes will cook and if they cook differently in these different environments. So in Denver, Colorado, the external pressure is about 0.85 atmospheres. In Honolulu at sea level, the atmospheric pressure is about 1.0 atmospheres. But in a pressure cooker, and you've seen these probably like instant pots that you can buy on Amazon, the external pressure raises to about 2 atmospheres. Now, if you'll recall, the boiling point is the temperature at which the vapor pressure of the liquid you're heating is equal to the external pressure. So in order for us to match different pressures here, we're going to have to heat these liquids, in this case water, to a different temperature. So at 0.85 atmospheres, the boiling point of water is about 70 degrees Celsius. In Hawaii, it's going to be 100. And in a pressure cooker, it's going to be about 120 degrees Celsius. And intuitively speaking, if we can cook a food at a higher temperature, it's going to cook faster. So if we were to examine the relative rates at which these potatoes cook, we'll see that this is the slowest. This has a medium cooking rate. And this pressure cooker is going to have the fastest. And that is how pressure cookers cook foods at higher rates. Because the apparatus is pressurized, in order for the water to boil, we need to heat it to a higher temperature because we need to increase the water's vapor pressure to match the very high external pressure that is present in the cooker. So that's why those sort of appliances are very useful in the household. You can cook things at a much faster pace. Let's get that out of the way. And that brings us to the distillation apparatus. So distillation, this term here, distillation is the separation of two liquids or more liquids. You can have an infinite number of liquids. That have different boiling points. And chemists in industry and in the lab utilize this technique to accomplish this. So first, let's examine this apparatus. So this is just the structure of what the apparatus will look like for a simple distillation. And let's label all the components. So here we have a thermometer. Here we have a cooling condenser, or sometimes just called a condenser. And the cooling condenser works by pumping water in through this hole and pumping it out this way. So this is water coming in and water coming out. And you'll see that occur in the experimental, in the second part of this video. This component here is called the still head, or sometimes called a distillation head. This right here is called a round bottom flask. And this is the flask where heat is applied. This component is called the vacuum takeoff adapter. And this component is called the receiving flask. And in reality, you can use whatever you want here. It doesn't have to be a flask. It could be a beaker, or in the experimental case, it'll be a graduated cylinder. So in terms of simple distillation, let's give a small example. Let's say that I have a two-component mixture, which I will represent using two different colored dots. I'll have an orange dot here to represent vegetable oil, which has a boiling point of about 300 degrees Celsius. Now, I'm going to represent a red dot with a gasoline, like you put in your car. And gasoline has a boiling point of about 200 degrees Celsius. Now, let's mix these two components inside of the boiling flask, or the round bottom flask. So I'm going to have some particles or some molecules of gasoline. And I'm also going to have some particles of vegetable oil. Now, as we discussed earlier, a substance which is said to be more volatile in general has a lower boiling point. So in this case, the gasoline is the more volatile component, and the vegetable oil is the less volatile component. Now in distillation, when you heat the mixture, the less volatile component will come over and distill over first, and the more volatile component will come over second. So the way this will work is you apply heat to this mixture and you're increasing the vapor pressure of both of these substances. So both of them are wanting to transition from the liquid state into the gas state. So you'll see these molecules climb up this still head here and they will hit the thermometer. And the thermometer will tell us what substance is coming over first. And we predicted that because gasoline is more volatile, it's going to come over first. So the way this might look is that these gasoline particles might travel up the still head as a gas, and eventually they'll reach the condenser. So here we have a hot liquid, a hot gas, but now because this condenser is being cooled by water, the gasoline is transitioning back from a gas into a liquid. And this liquid here will fall all the way down the condenser through the vacuum takeoff adapter, and you'll end up in your receiving flask. And that is the premise by which simple distillation works. So feel free to look at this to fill out your worksheet. All the components are labeled here. Now let's examine what happens when we want to separate a different mixture. And it looks like some of the ink has bled through. So let's get a fresh sheet of paper here. If we have a mixture that's a little different, in this case I'm going to use different colors. We'll use pink and green. Instead of using vegetable oil and gasoline, let's use some molecules that we're going to use in this experiment. So for the green molecule, this is going to represent a molecule of toluene, and we'll show you the structure of that later, which has a boiling point of 110 degrees Celsius. And for the pink particles, that will represent a molecule of cyclohexane, which has a boiling point of 81 degrees Celsius. Now you'll notice the difference between our first example here and our second example is that the difference in boiling points between these two substances is much different. Here we have a 100 degree difference in boiling point, but here we only have about a 30 degree. So there's a much narrower difference between what happens when these two substances distill. So let's see what happens. We apply heat to this mixture, but instead of just the gasoline coming over, in reality, both molecules will end up coming over at about the same time. So here we have an issue because we want to separate these two components, but when we try to utilize simple distillation to do so, we end up with a mixed solution, which is not what we desire. We want these to be completely separate in our receiving flask. So the way we get around that is by using what's called fractional distillation. This is a picture of a fractional distillation apparatus, and you'll notice that most everything is the same. You have a boiling flask, a round bottom flask, you have a still head, a thermometer, a condenser, and the vacuum takeoff adapter. The main difference is this component right here. And this is referred to as the fractionating column. And the purpose of the fractionating column is to increase the surface area that the liquid, that the gas is in contact with. And you'll notice here that the fractionating column actually looks a little bit similar to the condenser. And that's because in reality they are. it just has a little wider bore here to have a little bit extra surface area. But in reality, what you can do, and what we'll do in the experiment, is we'll utilize something like this. So this, you can see, is basically the same thing here, only it's being filled with this steel wool. And the steel wool will further increase the surface area that the gas molecules are in contact with. And the surface area will help us separate these components in fractional distillation. The more official way that this can be done is through something like this, which is called a Vigreux column. And this column has a bunch of small little glass indentations that serve the same purpose. These small indentations have a higher surface area, and they increase the surface area that the gas is in contact with. So let's examine how that functions, how that works. So we'll take our same mixture of cyclohexane and toluene and place it into our flask. And we're going to apply heat once again. And when we heat this mixture, it's going to come up mixed again. So let's transition here to a zoomed in image of what it might look like. So say, for example, we have this mixture here. That's traveled up the fractional column. Now, as it travels up the column, it's actually going to cool on the surface wall and turn back into a liquid. And once it turns back into a liquid, it's going to re-vaporize, and when it re-vaporizes, it will become more pure. So the proportion of the more volatile component will increase. So we said that the more volatile component in this case was the toluene. And I believe I screwed up the mixture. So in the previous example, the toluene was green and the cyclohexane was purple. So excuse this screw up here, but so just to make sure, the toluene is in green, and I'm just going to change the cyclohexane into orange. So what I said previously was that the more volatile component will increase as we travel up the column. So here we have 1, 2, 3 particles of toluene and 1, 2, 3, 4, 5, 6, 7 particles of the cyclohexane. So the cyclohexane population will increase, or stay the same rather. So we have 7, or right here we have, 1, 2, 3, 4, 5, 6, 7 molecules of cyclohexane. And then we have only 2 molecules of toluene. And if we continue this process of condensation and redistillation, you'll notice that the amount of cyclohexane will remain constant, but the amount of toluene will decrease. And you'll see that we transition from 3 particles of toluene down to 2, and now down to 1. And eventually when you reach the top of the condenser, it'll only be toluene coming over. So your first fraction that you will collect is mostly toluene. So the point being here is that using fractional distillation, we could separate a mixture which we could not normally separate using simple distillation. And the rule of thumb is that when your liquids have a boiling point difference of less than about 70 degrees Celsius, you need to use fractional distillation. And that brings us to the final part of the experiment, which is, why are we doing this in the first place? What's the purpose? So for this experiment, we're going to be playing with 3 molecules, one being acetone, and this is the structure here, and these are called zigzag structures. So here, here, and here, any point there's a point or a corner represents a carbon, and the O is the oxygen. So one of them was acetone. This has a boiling point of about 56 degrees Celsius. The second molecule we're going to be working with is cyclohexane. which looks like that, and has a boiling point of about 81 degrees Celsius. And then the final molecule is toluene. And this has a boiling point of about 110 degrees Celsius. And you'll notice that the difference in boiling points between these three is rather narrow. It's not like gasoline and vegetable oil, which is, about 100-degree difference. These are very close, so we're going to need to use fractional distillation to figure out what's here. Now, the point of the lab is that we're going to be given an unknown, and we need to figure out first which two of these compounds is in the unknown. And secondly, what is their relative percents? In other words, is it 50% of this component, or is it 50% of this component, or vice versa? It could be any ratio, 60% of this and 40% of that. We want to figure out what that is. Those are the goals of the experiment. And we will utilize fractional distillation, which we will film in the fume hood in part 2. Alright, so here we are in our fume hood, and we've got all the components we need to perform the fractional distillation. Here is the round bottom flask sitting on top of a cork ring, and that's what we use to keep the flasks from tipping over. And then we have here our fractionating column right here with the iron wool inside of it. We have our thermometer right here. We have our three-way distillation apparatus, or distillation head right here. We have our cooling condenser, which is not yet hooked up to the water. We have our vacuum takeoff adapter here, and our graduated cylinder, which we will use to collect the distillate in the distillation. And in the back we have some boiling stones, boiling chips, and we will use these to prevent the mixture from boiling too violently, and I'll describe that in a little more detail. And we finally have our unknown mixture B. So this is a mixture that contains two of the possible compounds, toluene, acetone, or cyclohexane. Okay, and we'll move over to the heating mantle to assemble the apparatus. Alright, so we've got our round bottom flask, 250 milliliters, and to it we're going to add our boiling chips. So I'm going to get a few of these. It only takes about 3 or 4, but it doesn't really matter how many get in there. So we've got about 4 boiling chips in there, and now I've measured out about 60 milliliters of our unknown sample B, and I'm going to add it to the round bottom flask very carefully. And now that we've added it to the round bottom flask, we can assemble the distillation apparatus. Alright, so we've added our unknown mixture B to our round bottom flask, and it's important that we added the mixture to the flask before we placed it on the heating mantle, because if we tried to place the flask in the mantle and then pour it in the solvent might leach into the heating element, which could start a fire. So it's always good practice to put in your whatever you're going to boil before you place it into the heating mantle. So as this said, we shall place it into the mantle, and on top we're going to place our fractional column, just like that. And then we'll tighten it to make sure it's nice and sturdy. Okay, now that that's in place, we'll place on our distillation head here, and on top of that we'll place our thermometer. As you can see, the bulb sits right in the vapor path, so we can get a nice accurate temperature of the vapor. And this is our, if I can get the hose out of the way, this is our cooling condenser, which I've now added the cooling lines. So this portion is where the water comes in, and this is the portion where the water comes out. It's important to have the water come in this way and flow up because it cools the vapor more efficiently when it goes opposite of the vapor path. So the water path is going this way and the vapor path is going this way. So we're just going to place that into here. And to secure this, to make sure it doesn't fall down, we're going to use these blue clips. They're called Keck clips, and they keep the joints from separating. And we're just going to tighten this down here. So now that that's secure, we can add our vacuum takeoff adapter and secure that with a Keck clip. Snap on just like that. Oops, almost dropped it. And now we have our graduated cylinder, and there's a little bit of a gap here, so we will take some of these cork rings to help elevate it. And here we have the assembled fractional distillation apparatus. Alright, so now that we have our assembled apparatus, before we can start heating, we want to make sure two things. Firstly, we want to check the joints to make sure that there are no gaps. So from what I can see, all the joints are sealed, and it should not cause any leaks. So if there was a gap between the joints, it might leak some solvent, and if you have solvent in the air, it could be a fire hazard or an explosion hazard. So all our joints are sealed and good to go. And secondly, we want to make sure that this exit line here for the cooling water is going to exit into the sink and not on the bench, or else it might flood the hood. So now that that's true, we can turn on the water, and you'll see that the water travels from this end to this end and exits to the other side. And now that our cooling water is on, we can turn on our heat to about 5 and begin heating the mixture. Alright, so as you can see, we've been heating for a few minutes here, and our mixture in the flask is starting to boil. And you can see the boiling chips are helping the boiling to make sure it's not too erratic. And in a few minutes, you should see, or actually you can see it right here. This right here is the vapor front of the mixture that is slowly climbing into the fractionating column. So right now, all of the vapor is mixing with all of the steel wool here. As you can see, it's continuing to climb up and up and up, right where my pen is. It's going up and up and up. Now, because it's already boiling, I'm going to turn the heat down to make sure we don't boil it too quickly. As you can see, the vapor front has now met this joint, and it's about to hit the thermometer. So right now the thermometer is at about 30 degrees Celsius. But once the vapor gets to it, it's going to jump up to its first temperature. So the vapor front is still here. Right there, I don't know if you can see it, right there. And it's about to make its way into the distillation head, and eventually it'll make its way into the condenser here. So here you can see it just met the condenser joint, and it's going to slowly make its way into here. And as you can see, it's already dripping, and it's coming into the vacuum takeoff adapter. And we should have our first drip of distillate coming through. Yep, there it is, the first drip. So now that we've collected a little bit, I'll look at the temperature, and the temperature looks to be about 54 degrees Celsius. So I will write that down. And I'm going to record the temperature for every 3 milliliters of distillate collected, and we'll get the data from that. So it's been about 30 milliliters of distillate we've collected, and for that entire time the temperature has remained at about 56 degrees Celsius. But now, I don't know if you can see this in the camera on the thermometer, if it will focus, the temperature has begun to increase to above 60. So the temperature is slowly climbing after the 30 milliliter mark. So that tells us that the component that's distilling over is changing. So in addition to temperature, the other indicator that tells you that the component is changing is that if you can see there's lines that appear in the graduated cylinder, and those lines are due to a difference in density between the two compounds. So when you see those lines appear, it's a good indication that the next compound is coming over and it's remixing in the graduated cylinder. So we've been collecting about 55 milliliters here, and for that time period, the temperatures remained at about 110 degrees Celsius. So now that there's 55 mils, and remember we started with 60 milliliters, we can assume that inside the boiling flask, there's probably only 5 or 6 milliliters. So now would be a good time to shut the heat off, because we do not want to boil the flask to dryness. When you boil the flask to dryness, you risk cracking the glass from overheating it, and another risk is that sometimes the solvent can have explosive impurities inside of it, and if you heat them too much, they could explode. So we're just going to call it done here and turn off the heat. And for the remaining 5 milliliters, we can assume that that would have remained at 110 degrees Celsius.